Now that we have gotten the preliminaries out of the way, let's start talking about some practical analog circuits. So an analog circuit is defined as a circuit that works with voltages that are continuously variable. So what we mean is we have a circuit that, say, has a power supply of, I'll just draw a battery here, and let's say that's a 12-volt battery. So that analog circuit is going to be limited to this 12-volt range, and of course we're probably going to put our black probe of our voltmeter here so that this will be by definition 0 volts. And so at this point here we'll have plus 12 volts, and we're going to have a little bit of overhead, meaning that we won't be able to get the entire 12 volts in there. So let's say, for all practical purposes, this circuit can work between, perhaps 0.1 volts and 11.9. So we can't quite get up to the 12 volts, can't quite get down to 0. Some circuits can, some circuits can't, and we'll talk about those down the road. But the point is that there is a range of voltages that we are limited to. And just to make things simple, let's just assume we can go all the way down to 0 or all the way up to 12. So this particular circuit will have voltages in there anywhere from 0 volts to positive 12 volts. And by analog, we mean that we can have any voltage in that range. So I could have a voltage of, how about 10.37245, or I could have a voltage of 8.13512. I'm being kind of ridiculous here with my how far I'm going down the decimal points, but I'm showing that I can have any voltage that is within that range. So we can go to positive 12 volts or to 0 volts. And we can very finely divide what those voltages are. So let's take a look at an example of what I might be talking about. Let's say I have, how about a temperature sensor? Let's put that as a thermistor here. And let's say that that particular thermistor, let's put some bias on there. So we need some kind of a voltage to get it working, and we can pick off a voltage there. So there's our ground, there's our pick-off voltage. And let's say that at 100 degrees C, we have, how about, let's say we have 5.62 volts. And at 0 degrees C, we have 4.38 volts. So there's a very narrow range, and what I need to do is have a circuit that's going to make a change that is more meaningful. So what I'm going to do is send that through an amplifier, which I will represent with just the general amplifier signal. This is going to be a number of transistors or whatever. It might be an integrated circuit. Most likely it's probably going to be an op-amp. But let's say that this circuit conditions that such that now when I'm at 100 degrees C, I now have, how about a nice even 10 volts? That'd be convenient. And at 0 degrees C, let's say I have 0 volts. So I'm using an amplifier to change that voltage range. So we usually think of an amplifier as something that makes things bigger, and this absolutely is. It's making it a range of 10 volts instead of a range of less than 2 volts. So it does increase that range, but notice that our lower voltage goes down and our higher voltage goes up, giving us this particular range of output, which would be really nice if we could stick a voltmeter on there basically, or calibrate a output circuit like a voltmeter and just simply say, okay, 10, we'll just have it say that's 100, and at 0 it just says 0. So that's a way of using an analog circuit. So we're taking a narrow range of voltages from this thermistor circuit and turning them into a wider range and using some bias such that we get some nice numbers that we can convert into some simple voltages here to display as a temperature. So that's one possible thing you might do with an analog circuit. But notice we can have any voltage in this range here and spread that out to any voltage in that range. So the difference between an analog circuit and a digital circuit, which we will talk about another day, is that a digital circuit is only going to have two possible voltages. Those voltages might be 0 volts to plus 5 volts for what's called a TTL circuit, or other circuits might have minus 12 volts to plus 12 volts. But we don't have a range in between. We can't be 3.761 volts. Well, if we are, it's going to interpret that as either 5 volts or 0 volts. I don't want to go into much detail about that here because we will talk about that in digital circuits. But the point is it's going to be one or the other, and if it's somewhere in between, there's going to be a threshold where anything greater than, let's say, 4.25 volts is going to be increased by the circuitry to be 5 volts, so it's going to take that up all the way. And let's say anything less than 1.25 volts is going to be pulled down to 0 volts. So it will not allow us to be anywhere in between. It can only be one of those two voltages. So that's what a digital circuit is. And to do something like with the thermometer, we would have to have a number of sets, the number of wires, several wires with either 0 volts or 5 volts, 5, 0, 0, or 5, one or the other, one or the other. Or it could be the minus 12 or the plus 12. So we can have one voltage or the other in a digital circuit, but in an analog circuit we can have any voltage in between. So that's the basic idea of an analog circuit. So we have already worked with one analog circuit in the lab where we put all the components together to make a power supply. Well, that was an analog circuit. And talking about analog circuits, there are basically three types of analog circuits. Might be able to find other types, but these are the basic three types. One is DC circuits. And once again, with the power supply, we've already dealt with the DC circuit. In that case, we had the power supply, which I'm not going to go through the whole circuit at this point, but eventually we had an output that was plus 12 volts, and we had a regulator that when we changed the load, so there's a variable resistor representing the load, if we decreased that resistance, therefore pulling more current out, normally we would have a voltage drop, but the regulator would boost that back up to hold that at a steady 12 volts. So that's one type of a DC circuit. Another type is what we just talked about, that circuit with the thermistor. So we had a DC voltage that would vary with the temperature. And so the DC voltage may go up and down, but it doesn't do it in any kind of a periodic change. So it goes up and down slowly, but doesn't go up and down and up and down and up and down like we're going to talk about in a moment. So those are DC circuits that have a steady voltage that may rise and drop, but not with any kind of a frequency, which we'll be talking about in a moment. So that's DC analog circuits. The next type would be both AC circuits, meaning we have alternating current. So AC, but we aren't talking about the AC that comes out of the walls. We're talking about AC from oscillators or microphones or other circuits. And that falls into two different types. We have audio frequency circuits, or AF, and we have radio frequency circuits, or RF. And the difference is the range of frequencies that we work with. So let's take a look at audio frequencies first. So let's imagine that my pin here is a microphone. Inside there is a diaphragm that vibrates when air vibrations hit it. So I'm talking, I am producing vibrations in the air. Those vibrations coming from my voice are probably anywhere from 100 times per second, or 100 hertz, to maybe 4,000 times per second, or 4 kilohertz. But our ears can hear a range of frequencies anywhere from 20 cycles per second, or 20 hertz, all the way to 20,000 cycles per second, or 20 kilohertz, at least a normal person. If you are ill, you might actually hear slightly higher frequencies, if that makes any sense. So audio frequencies, or AF, are going to be frequencies between 20 hertz and 20 kilohertz. And to finish my explanation about the vibrations in the microphone, I'm talking, producing a lot of different vibrations of all kinds of mixed frequencies, and that's causing that diaphragm to vibrate, and that diaphragm in a dynamic microphone is going to have a coil of wire in a magnetic field, and that's going to cause a current that is proportional to that vibration to come out. Alexander Graham Bell called them voice-shaped currents. And there are other types of microphones too, but let's just look at the dynamic microphone because that's the easiest to kind of wrap our minds around. So as I'm talking, that diaphragm is going back and forth. And as it comes toward me, it's going to cause, let's just draw a little coil of wire here representing that wire. There's our diaphragm that's vibrating. There's a magnet in here just to make it complete. So that coil is vibrating in that magnetic field when it's coming towards me or going that way. I'm going to get a current that goes in one direction. What direction depends on which way the magnet is oriented and which way the coil is wound. I'm going to get a current that goes in one direction through that coil. And when that coil is moving away from me, so it comes toward me, I get current going one direction. It goes away, I get current going the other direction. So I get current this way, that way, this way, that way, in a continuous change in direction of current. And I have a number of complex frequencies. Let's say it's just a simple sine wave. I'm going to have a voltage that goes up and down and up and down. What's the range of this voltage? Well, from a microphone, it's going to be pretty dang small, just a few millivolts, but it's going to go up to some peak voltage, and that's going to be determined by how much current is coming out from the microphone and what load is on it. And it's going to go down to some other voltage. And in the case of the microphone, we're going to be looking at, in the middle, it's going to be basically 0 volts. So it's going to go up to a voltage, up to a positive voltage, and then down to a negative voltage over and over again. That's a single frequency. But what's coming out of my mouth is a very complex range of frequencies. We have low frequencies and we have high frequencies. So I'm representing that. This is time going this way. So I have another video where I explain what waves are. We call these waves because they look like waves on an ocean or ripples on a pond, but they're actually voltages going up and down with time. And so if they go up and down fast, we have a high frequency that's going to be a higher pitch. And if they go up and down slowly, that's a lower frequency or lower number of transitions per second, and that gives us a lower pitch. And I have all sorts of powerful high frequencies and not so powerful low frequencies, all kinds of things mixed together. And if we could look at that on an oscilloscope, we would see them mixed together to look maybe, just off the top of my head, maybe something like this. Just a repeated pattern of, that sort of looks like a heartbeat, doesn't it? But we would get a repeated pattern that's a mix of all these different frequencies. And we'll talk more about what is contained in those when we get deeper into audio frequencies and audio frequency circuits. And so this contains, from my voice, maybe frequencies as low as 100 times per second or 100 hertz up to maybe about 4 kilohertz. But once again, we can hear a range all the way from about 20 hertz to 20 kilohertz, and that's called the audio frequency range. Now, when we think about that, what would you think the middle of this range is? Well, between 20 hertz and 20 kilohertz, we would think that's about 10 kilohertz, wouldn't you? But that's not the way we hear things. The way we hear things is logarithmically, and you should have just recently watched the video about logarithms and know that we would use a logarithmic scale to plot this because that's a convenient way to squeeze a wide range into a small space, but also we hear logarithmically, and so that makes a lot of sense. So if you want to get an idea of how we would plot this or how we would imagine it, is think about a piano keyboard. And if you take about a handspan on that keyboard, you're going to play notes that are about an octave apart. And so if we have an A, which is 440 hertz, and we're hitting that A on the keyboard, a hand's width away is another A, and that would be 880 hertz. So notice that the lower pitch A and the higher pitch A have a halving or a doubling of the frequency. And so the next lower A would be 220 hertz. And these are the ones that are kind of easy to do. I don't have to do much math in my head to show these. So we have an A to an A, and then an A to an A, and they're the same distance on the keyboard. And so that's the way the logarithm works. Remember, with the logarithmic scale, if we double the frequency, we simply have the same distance. So it's like a piano. A to A to A, double the frequency, double the frequency, double the frequency, same distance on the scale. So if we do that on the audio scale, we find that if I put some lines here, these are evenly spaced. They're actually going to be a factor of 10 from each other. So let's make this one, let's put one over here, make that 10 hertz, and make this 100 hertz. So we're going up by a factor of 10 here. Make this one 1,000 hertz. This would be 10,000 hertz. And that would put 20,000 hertz, let's see, we want to be about a third of the way over here. So right about here, let's put that up here, 20 kilohertz. And then down here, 20 hertz would be about the same distance, right about there. 20 hertz. So if we double this distance from 10 hertz to 20 hertz, double that, that's to 40 hertz, then to 80 hertz, and then 1600 hertz. So we keep doubling the frequency, we double the distance, and we would get those frequencies spaced around there. And notice how once we've done this, from 20 hertz to 20 kilohertz, let's draw a line somewhere in the middle, right about there. Well, that's going to put us right around, well, let's see, 20 hertz. It's going to put us around 400 hertz. 400 hertz is a little bit low to use as a test tone, so we kind of kick that up to about 1,000 hertz, and that is your typical audio test tone. So that's your audio frequencies from 20 hertz to 20 kilohertz. The next thing we have is radio frequency. And radio frequencies, depending on who you're talking to, that could be 20 kilohertz and above. Some people might say 30 kilohertz and above, but I really think those should be called ultrasonic. They're higher than our hearing, but no, dogs can hear some of them. And as we go up in frequency, we're going to get to a point where they become practical to use as radio signals. So radio frequency, typically we talk about around 100 kilohertz. And that can go all the way up to, what's the top of the range? I think it's 300 gigahertz. And above this frequency, it's not practical to make circuits that work with them, although they are starting to find ways to work with higher frequencies. But eventually we're starting to get into the frequencies that light is made from, such as infrared and visible light, which are up in the terahertz range. But this range of frequencies is called radio frequency, or RF. Now it's such a wide range, that's quite a bit, 100 kilohertz to 300 gigahertz. How close would I have to put my lines together to fit that even in a logarithmic scale? Pretty close together. And it's not practical to make a circuit that can work in this entire range of frequencies. So we typically work with circuits that are in some subset of this range. And so we have ranges from what's called low frequency to medium frequency to high frequency. If we get to VHF, or very high frequency, that starts at 30 megahertz. So now, knowing that, I can say, well, that's going to be around 3 megahertz. Medium frequency would be 300 kilohertz. And low frequency would be about 30 kilohertz. The next one above is UHF, which starts at 300 megahertz. And so we have these ranges of frequencies. Basically, I should probably draw the lines more like this. These are the starting frequencies. So 30 kilohertz to 300 kilohertz is low frequency. 300 kilohertz to 3 megahertz is medium frequency. 3 megahertz to 30 megahertz is high frequency. So these are the starting frequencies of each of those ranges. And notice we're still very far below our 300 gigahertz. Then we have 3 gigahertz, 30 gigahertz, and I just ran out of room. And once again, we see this is a logarithmic scale. I've multiplied by 10, I'm going the same distance on the board, and to get to 300 gigahertz I have to be just a little bit off the board over here. So we typically have circuits that work in one of these ranges or even just part of that range. So just to let you know where things are, FM broadcasts are somewhere up around here at roughly 100 megahertz. AM broadcasts are somewhere down in here, like around 1 megahertz. In the United States, our AM broadcasting band is centered on 1 megahertz, but they may be different in other countries. And so there's AM, FM. Above there we have aircraft and other types of communications. And down in this area we have military communications and ham radio that want to go long distances. We get up into the gigahertz range, we're going to have things like cell phones and such that use these very high frequencies. And also Wi-Fi is up in this area here too. So very high frequencies, very low frequencies, and we have different circuits that will work in these different ranges of radio frequencies. Now there are other frequency ranges like VLF, very low frequency, which of course would be around 3 kilohertz. So I'm running out of room again. Very low frequency, I forgot what comes after that, extremely low frequency or something like that, which would be around 300 hertz. We're getting down into the audio frequency range here. And so, yes, you can do radio at that range, but there are problems with it. And notice that I'm also 30 kilohertz, I'm barely above the audio range. So our audio frequencies are somewhere right around here, from 20 hertz to 20 kilohertz. So this does show radio frequencies at 30 kilohertz. We can have radio frequencies anywhere, but for practical purposes, we start at around 100 kilohertz. But we can actually be anywhere, and if you can create radio waves at that frequency, you are in a radio frequency. So you can see there's quite a range of frequencies there. So there are different problems working at different frequency ranges. The main problems we have are when we get to very high frequencies, we have a problem with what's called stray capacitance. So what is a capacitor? Here's the symbol for a capacitor. That is 2 lines separated by a gap, and that's because a capacitor is 2 conductors separated by an insulator. And what does this do? Well, we've talked about this in detail in the DC circuits. When we change the voltage across there, we get a sudden surge of current through there, and then it builds up a charge on the 2 plates, and once it builds up a charge, the current stops. And with alternating current, well, every time we change the voltage across there, we get a surge of current through. We flip that voltage, we get another surge of current through. And the more often we change that voltage, the more often we flip it, the more current goes through. So at higher frequencies, we get less capacitive reactance. In other words, the capacitor is blocking it less. And so we get to the higher radio frequencies, and we have a problem that on circuit boards, we have parallel lines going to different parts and different components of the circuit board. Conductor, insulator, conductor. Looks like a capacitor to me. Very high frequencies, well, we have a low capacitive reactance, so we can get currents flowing between those traces on the circuit board. Or we just have some parallel wires. Same thing. We get to higher and higher frequencies, we get more and more currents going between those because of the capacitive reactance getting lower, and we get leakage through these parasitic capacitance. So parasitic capacitance is capacitance that exists where we don't design it, but just because of the nature of what a capacitor is, we get capacitance. Components have parasitic capacitance. A transistor or a diode has a junction, and there's conducting area, insulated area, conducting area. We expect it to be non-conducting across that junction, but because there is capacitance, we get some conducting through there. In fact, at high frequencies, you will often see a transistor that normally looks like that. Let's make an NPN transistor. And they say, well, at high frequencies, it looks like this. Because we have capacitance in the junctions of the transistor, so we get leakage currents from the collector to the base and from the base to the emitter and vice versa. So we get problems at higher and higher frequencies, and we have to mitigate that. We have special components that have less capacitance so they can work at higher frequencies. And we have to design our circuit boards to avoid these parallel traces. And sometimes you'll see circuit boards have little metal boxes here and there. And that is to block some of the radio frequencies from getting from one part of the board to the other. So as frequency gets higher and higher, we have more and more trouble mitigating the stray capacitance. But as the frequencies get lower, well, then we have another problem, because to get the circuits to work the way we want to, we need bigger capacitors and bigger inductors to work at lower frequencies. And so things start getting big when we get to lower frequencies. So there are things to deal with at the high frequency end and the low frequency end, and the circuits are designed to work in the frequency range they're designed for, and we'll talk more about that when we get to actual working circuits. So that's the basics of analog circuits. An analog circuit, by definition, is a circuit that has a continuously variable range of voltages available between two limits. And we can have DC circuits where that voltage remains pretty much steady. It may rise or fall depending on what's going on, but it doesn't have any kind of a period or frequency where it changes on a regular basis. Then we have analog circuits that do have a periodic change, such as audio circuits, like my signal from my microphone. We get vibrations anywhere from 20 hertz to 20 kilohertz, and circuits designed to work with those frequencies. And of course, those oscillations stay between the voltage limits. And when we talk about amplifiers, we'll see what problems happen if we get out of those limits. We get what's called harmonic distortion. And then we have radio frequencies that work, well, virtually anything can be a radio frequency, but typically we think of radio frequencies as 100 kilohertz and up to 300 gigahertz, where we have certain problems with the lower frequencies. Components get kind of large. Higher frequencies, we get stray capacitance we have to deal with. And we'll talk about that when we get into communication circuits. So I hope you found this useful and informative. And if you did, please give me a like down below. Give me a thumbs up. That really helps the channel, helps other people find these videos. And be sure to subscribe and hit that gray bell over there when you do, so that you get notified when I put up new videos. And a big thank you to my patrons at Patreon and my other donors. I could not make these videos without your support. And be sure to go to Vocademy.net and take my free course in electronics technology, where this lecture is one of the lectures in that course. Again, a big thank you to my patrons at Patreon. Couldn't do this without you. And thanks to everyone for watching.